So this is the last day of Eurocrypt, and so we will begin with the first session about side channel countermeasure, and we will have 3 talks during this session. The first talk will be is entitled Generalized Phase Ciphers for Efficient Prime Field Masking, and the authors are Lorenzo Grassi, Loïc Mazur, Pierrick Méo, Torben Moss, and François-Xavier Sandert, and Torben will give the talk.
Thank you very much for the nice introduction. So this is a joint work with my co-authors Lorenzo from Rouen University, Loïc from University Montpellier, Pierrick from Luxembourg University, and FX from UC Louvain. I'm sure most of you are familiar with the concept of masking, but essentially if we mask a symmetric encryption algorithm, for example, we don't process the raw data, the raw inputs directly, but we operate on a shared representation of inputs and state. And this shared representation is randomized for each execution, for each encryption. And if I, as a side channel adversary, want to extract some intermediate value, I need to either implicitly or explicitly learn information about all of the shares to target this intermediate value. And what we assume for masking, which is also well reflected in reality, is that side channel adversaries can only make imprecise observations. For example, they learn the Hamming weight of a share through the power consumption, and masking is able to amplify this precision. So let's say we have one share, we know the Hamming weight is 0 or 1, so we have a rough idea on the probability distribution of this intermediate value. Now if I add more shares, the second share has Hamming weight 1, the probability distribution is already more uniform, and this is more and more amplified if I have more and more shares. So we pay something, more shares, and we get some more security for that in return. Now, does this always work? Unfortunately not. So here's an example based on Boolean masking on the left in green and prime field masking on the right in red, orange. For 2 to 6 shares, and it's plotted an information theoretic plot of the mutual information over the noise variance. A high mutual information means we have low security, low mutual information means we have high security, and what we can see is that for Boolean masking in the green plot, I need some certain noise threshold to really kick off this security amplification. If I don't have this noise threshold, then basically for any number of shares, I leak the same amount of information, which is really bad because I still have the cost that I invested. Yeah, this is exactly the zone which is critical. Just to have like a concrete example on a very small field, so f2 to the 3 and f2 to the 3 minus 1, so that the top row of distributions is for this Boolean masking, the bottom row is for additive prime field masking, and we can see that in the top row we never really approach a uniform distribution because the Hamming weight of all shares still leaks the parity of the Hamming weight of the secret to me, regardless of how many shares I have. So I can increase that as much as I want. It doesn't help me with security, while on the other hand, for prime field masking, we don't have this situation, and we approach a uniform distribution, even for these noise-free Hamming weight leakages. So what's the state of the art in this field of prime field masking? At TCC 2016, Dembowski et al. Found that they proved that masking in groups of prime order can amplify arbitrarily low noise levels. This is because you don't have any non-trivial subgroups if you have a prime order. And what this means, what it gives you, is that you get exponential security in the number of shares in presence of any non-injective leakage function. Injective leakage function would be like the identity leakage, then you don't have anything to protect because the adversary already has all the information. Then last year at Eurocrypt, we presented an information theoretic evaluation of these properties, especially with respect to Hamming weight and bit leakage, and presented some first practical results. And we did this on the hands of a toy cipher that we built, this AES prime, which was based on a small Mersenne prime and a bijective power map as the S-box. Then at CHES 2023 last year, there have been introduced very efficient masked gadgets for the squaring operation. The squaring operation is only nonlinear in prime fields, not in binary fields. That's why they cannot be used by most typical block ciphers, but if you operate over a prime field, you can use this as a source of nonlinearity. And then in the talk from Monday, given by Elena, we have learned that Hamming weight leakage functions, in presence of Hamming weight leakage functions, the security of prime field masking can be approximated by log p to the d. So I have this size of my field as a security parameter. What has been missing so far, like a really efficient, lightweight primitive that is able to take advantage of these cool properties that prime field masking can give you. And this is what we have done to demonstrate this is like a relevant research direction, and we can leverage these potential advantages. So what we have done is we introduced the FPM, Feistel for prime masking, family of tweakable block ciphers based on a generalized Feistel structure to get like cheap and efficient inverses. We propose then a concrete instance of this general family of ciphers, and we compare it to Skinny. We chose Skinny because Skinny also has different versions with different sizes of the tweak, so the comparison kind of works best in that regard, and we look at the efficiency and the security. So our new family uses the Tweaky framework and is based on an LED-like design to simplify related tweak analysis. So on the left side, you have like the normal block cipher, where there's no tweak, and the key schedule is just I add the master key whenever I have the key addition. And in the middle, I have the tweak size is the same as the key size and the state size. And on the right side, I have the tweak size is twice as large as the key size. LED-like design, because between each tweaky addition, I have multiple rounds, not only one, but multiple rounds in a row to get like stronger properties between each tweak addition. The rounds itself, we have chosen to instantiate with a type 2 generalized Feistel. Feistel because we want cheap inverses, type 2 because it gives the best properties, and it's basically defined by two parameters, B and C. B is the number of branches, so like the number of Feistel branches, so the large ones going different directions. And C is the number of field elements per branch. Why we need that you will see in a second. So on the left side, it's 2 times 2, 2 branches and 2 values each. In the middle, we have 2 branches and 4 elements each, so also 4 inputs going into my F function of the Feistel. How do we instantiate this F function? There we use 2 layers of power maps, so 2 nonlinear layers at the beginning and at the end, with a linear layer in between, which is usually instantiated with an MDS matrix multiplication. And we want F to be bijective to avoid collisions at the output to simplify security analysis and to provide full nonlinear diffusion. The cool thing about this structure is its type 2 generalized Feistel structure is that we can use power maps which are not bijective in the field. Let's come to the concrete instance we have built, which is called small p square, and it's designed for efficiency in hardware. So here we have the state. The state is defined by 4 times 4, so 4 branches of 4 FP elements, where the prime is 2 to the 7 minus 1, a Mersenne prime. It's the same one that has been used for the AES prime because it really gives you efficiency in hardware. And the full size is then 4 times 4 times 7. It's 112 bits, so we also claim 112-bit security. And the tweak size is tau chosen from 0, 1, 2 times 112. Now, the concrete F function of our small p square, this is probably the most important slide of this talk. We have chosen an invertible MDS matrix with a low depth and number of additions, which has been discovered by Duval and Laurent at TOSC 2018. It is based on a Feistel as well, but this is only a coincidence. This is not a requirement of the design, so that even like the middle MDS matrix looks like a Feistel is only a coincidence. But the good properties is that it only requires 8 additions and a depth of 4 additions, while the multiplications by a constant are only by a constant, which is a power of 2, which in a Mersenne prime field means just a rotation of the bits, which is completely free in hardware because it's just wiring. And then the important part is that we have instantiated the power maps at the beginning and at the end by a squaring. So because of these very efficient squaring gadgets introduced at CHESS last year, this whole construction is very efficient, in particular asymptotically, because squaring gadgets are half as costly as a multiplication. This entire construction asymptotically has the cost of 3 multiplications only, which is like very cheap, and we still get higher degree and better properties than if we would actually use multiplications instead of squarings. Now this one I will skip for a second. The hardware cost, when the implementation is masked, we compare so we were looking in the literature for a skinny 128, 256 implementations, because it's like the comparable setting to our small p square with tau equals 1. And there are not really any securely masked implementations publicly available, so we used a tool introduced at CHESS 2022, which is called a GEMA, Automated Generation of Masked Hardware, and we used it to derive those masked implementations and then compare against them. And like the main story is that we, with small p square, we are more efficient than in area and latency and power compared to the skinny implementations. We need slightly more randomness, but recent research shows that randomness for hardware masking is not too expensive. And our efficiency advantage is mostly for like lower frequencies. Once you need really high frequencies, then these bit-level masked implementations of skinny are indeed better, because they anyway have a very short critical path. Now this is about a public implementation which was not of skinny 128, 256, but about the variant used in Romulus 384 plus, and we turned it into the 256 variant, and then compared once again our small p square to the skinny implementation. This one actually uses like a clever trick to have a very efficient implementation of the skinny 8-bit S-box, and we can see that even with that handcrafted implementation, we are kind of on par, slightly better at lower frequencies and worse at higher frequencies. Generally, the story is not that we claim that we have better efficiencies than skinny, but only that we are in the same ballpark, right? That we have kind of the same efficiency in hardware, and that there is not a huge difference in moving to these prime field operations. And remember, we get decryption on top for almost free because we use a Feistel. For skinny, this is not the case, SPN-based block cipher, so there you would have an overhead of 100%. Some side channel security evaluation. So on top we have the signal to noise ratio. We can see that's basically the same, it's only exemplary for a certain share. Then you have the t-statistics and Saska attack, which is giving us the rank of the correct key candidate. And what we see in the t-statistics and the Saska attack is that we basically get around 1 order of magnitude security advantage. This is for 3 shares. The advantage increases for a larger number of shares. So really, at some point, you have 2 orders of magnitude and so on. And the interesting part is we know that stronger attacks only get better, right? We know that stronger attacks will only widen this gap, because stronger attacks means lower effective noise level, and the noise level is hurting the skinny implementations, so the masked Boolean implementations much more than the masked prime field implementations. So yeah, we are confident that this is that you have very strong advantages in practice for these prime field masked implementations. We have a GitHub repository with like 40 different implementations of this small p square cipher. It sounds a lot, but the differences between many of them are only minor. This has also been accepted as a Eurocrypt 2024 artifact. Thank you very much for introducing that this year. And sorry to Martin for miswriting artifact. The good news is there's still room for improvement, because we are still using in the hardware code the standard addition, multiplication, and subtraction instructions, and then the Mersenne prime reduction trick. So if you implement dedicated versions of single operations. There's probably not much room to improvement, but chains of operations in a row, for example, in this matrix multiplication, then I think there is still a lot that can be improved, especially with critical path and area. Now, this is a teaser to recent work we have put on ePrint on the fault security that prime field masking gives you. The interesting thing is that even with respect to some fault attacks, you actually get significant advantages without doing anything extra, just from prime field masking automatically, especially with respect to CIFAR1 attacks. I don't know who is familiar with those. It directly gives you exponential security amplification in the number of shares. So the conclusion, we introduce a general design strategy for tweakable block ciphers, which are specifically optimized for prime field masking. We have built this first instance, a lightweight tweakable block cipher for hardware implementations. The design is competitive with state-of-the-art binary ciphers in terms of performance, and it can deliver much higher side channel and potentially fault security. The source code is online, and like future work would be deriving instances which are more optimized for software implementations, for example. Generally, we believe that these prime ciphers specifically made for efficient masking are very promising research direction for physically secure cryptography. Thank you very much.
So, is there any question? Yeah,
thanks for the talk. I wonder if you compare to also the non-tweakable version with AES, where does it fall in terms of performance?
Oh, do you mean the AES prime or AES?
No, normal AES.
Normal AES. So we're like area-wise probably factor 4 to 5 better. I mean, unmasked, we have a larger latency because we have more rounds. Masked depends on your AES implementation, really. But I would expect something like 3 to 4
yeah, and
factor.
Do you think with maybe like higher order you will see like skinny AES will become better, but maybe at later stage, or no?
This one I didn't understand.
Like in skinny, and when you increase the frequency. The frequency becomes better at some point.
Yeah, I mean, this frequency difference always depends on the way you mask. And like for skinny, you mask each nonlinear gate in the S-box, so each 2 input gates separately. And these gadgets have naturally a very short critical path, so you can automatically clock them at high frequencies. If you have some AES implementation based on Galois field decomposition or on multiplication chains, this might look different, and then there is also not much of a difference in terms of frequency.
Thanks.
Okay. If there is no more question, maybe I will ask one. I want to know if so you have the masking is an additive masking or Boolean masking?
Yes, so it's additive masking in the prime field. So you add modulo the prime.
And you can do all your operation on additive sharing, or you have to switch between?
No, I mean, the purpose of this cipher is really that you can do it completely in additive prime field masking without any conversions to Boolean or any other weaker type of encoding.
Okay, and one last question. So you propose 1 or 2 order masking, I think, in the T evaluation.
What do you mean?
So the order of the masking that you implement, it was 1 or 2nd order masking.
Yeah, we have 2, 3, and 4 shares for 1st, 2nd, and 3rd order security.
And how the complexity of the masking increase according to the order?
I mean, it's quadratic.
It's quadratic.
So it's, yeah, because we have squaring instead of multiplication, it's still quadratic overhead in the number of shares, but half compared to a multiplication for 1 squaring. So that's like the main advantage.
Okay, so thank you very much, Darman.
Yeah.
Yeah.
Sorry. So, like, of course, I mean, there's all sorts of primes, and they are like good primes, good-looking primes, and very ugly primes with high Hamming weight. Like when you are if you change around the prime, what does that do to your complexity?
I mean, I think Mersenne primes are really hard to beat, and in the small numbers that we care about for these ciphers, there are sufficiently many Mersenne primes, so you don't have any incentive to search for something like generalized Mersenne primes, Montgomery, whatnot. I think generally Mersenne primes are probably the best choice if you have them available at the size that you want. If you don't, then other approaches are fine as well.
Oh, thank you. I'm just asking because, I mean, all these problems with masking Kuiper is like if you can have somehow 3229 or the dilithium prime, then, but those are not Mersenne primes.
No, yeah. I mean, it depends then on the efficiency. But yeah, it would be an interesting avenue to, for example, replace the hash function you would use in these lattice-based schemes by a hash function that automatically works over the same prime field that the rest of the implementation uses, right? That could be done. I don't know how much of an improvement you would see through that. That needs to be determined.
Thank you.
Okay. If there is no more question, maybe let's thank Torben again. Yeah, so the second talk will be online. And yes, Elizabeth is not yet available, I think. Okay. Okay. Yeah.
Do you want me to start? Okay. Right? Okay, then I will get going. I hope you can hear me all right.
Yeah. Let me introduce you, Elizabeth. So the second talk is a novel framework for explainable leakage assessment, and by Shigao and Elizabeth Oswald, and Elizabeth will give the talk.
Yeah, okay, thank you very much. Hello, everyone. I'm going to talk about joint work with one of my former colleagues. We kind of looked at a somewhat strange question, and this is how could we combine a notion of explainability with a process called leakage assessment. And perhaps these terms are sufficiently unfamiliar, so that I want to get started by, first of all, talking a little bit about what this process of leakage assessment is really about. And I want to put this in context with the real world. And then once we have kind of done that, I hope you will kind of understand that there's a problem with a lack of explainability in this whole process of leakage assessment, which then motivates our work. And I will then briefly talk you through the key ideas that we used in our paper, and then I will just apply this to an example that hopefully is familiar enough so that you can kind of enjoy looking at the example with me. So where does leakage assessment really come into play, and does it matter anywhere? So in the real world, we use a lot of embedded devices for all sorts of purposes, and often they have to satisfy not only functional requirements, but they also have to satisfy certain requirements around security, and in particular cryptography. So these devices that I'm talking about, we use them really every day in banking security. We use them as travel cards, as ID cards. They're in passports. They're literally everywhere. And the devices that I'm talking about here, they typically have an embedded processor integrated. And actually, this is not just any old embedded processor. It's something that in the community we call a secure IC, a secure integrated circuit. So these kind of processors are built really very specifically with security in mind. And when you do that, then this isn't just about implementing cryptography efficiently, but this is also implementing cryptography in a way that side channel leakage is minimized. And of course, people also look at fault attacks. But what we do here focuses on side channels only. So these kind of products, before they can actually enter the market, they must undergo a process called security certification. So what is that about? You will notice I often use the word certification and evaluation interchangeably, and I just want to briefly clarify what means what. So certification is a process by which a certifier, which tends to be a national authority, kind of grants a certain certificate, security certificate, to a product. And a product could be a device, so a mix between hard and software, or it could just be a piece of hardware, or it could just be a piece of software. So there's everything, in a sense, can be certified. And this whole process pans out that the manufacturer of a product, which also pays them for the whole process, approaches a national certifier and also an evaluation lab, which is independent to the certifier and to the manufacturer. And the evaluation lab will then perform some form of structured testing. And how exactly they test depends a lot on the kind of certification scheme that the manufacturer wishes to have their product certified under. There are different schemes out there, and they often work with very different, they work in very different ways based on very different assumptions of how a certification should sort of proceed. The two main schemes that there exist are sort of either attack-based schemes. They typically fall under an umbrella term called common criteria certifications, and how exactly they pan out for secure ICs is kind of governed by a stakeholder group, which kind of comes together to evaluate attacks, so stuff that we publish in our community, countermeasures, and they then come up with a sort of a structured list of attacks that evaluation labs have to perform, and a scoring system by which they then kind of decide whether a product is secure in a certain sense, so according to a specific certification scheme or not. In contrast, there's a completely different philosophy out there as well, and this is kind of encoded in the American FIPS 140-3 standard. Here, an evaluation, so the certification scheme does not require an attack-based evaluation necessarily, but for the specific context of implementations of symmetric encryption schemes, and it really applies to these only, the standard actually says that instead a so-called non-specific detection process should be carried out. And this non-specific detection process is what we call in our community also often leakage assessment. Now, the advantage of attack-based evaluations is that they can be very thorough. You kind of, evaluation labs try to instantiate sort of the best possible adversary that they can come up with. But of course, you have got a little bit of a question mark hanging over. If none of the attacks work, you can still ask the question, well, maybe another version of an attack could have worked. So there's no way of completely, covering perhaps all possible attack vectors. This non-specific detection idea tries to kind of hone in on that, and it is based on a process that identifies potential information leakage independent of any concrete attack vector. Now, this kind of sounds really good, and I will explain to you very briefly how this is typically implemented. So the method that FIPS 140-3 sort of refers to is what we call in our community TVLA, Test Vector Leakage Assessment. And it's based on a very simple sort of idea. And the idea is as follows. So suppose we are testing an implementation of a symmetric encryption scheme. We can typically supply inputs to this implementation. Now, suppose we supply two different inputs. The question is, could we or can we distinguish the corresponding side channel measurements? So we may have two distinctive inputs, and we kind of sample multiple side channel traces from each input, and then we ask, are these two trace sets distinguishable statistically or not? If they're not distinguishable, then there seems to be no connection between the input and the traces, which would indicate no information leakage. If we can distinguish these two trace sets, then there is information leakage. So this is the principal idea. And then this, of course, needs to be translated somehow into a concrete statistical testing process, which is what the TVLA document does, and which is also what the version of FIPS 140-3 does. And there are all sorts of assumptions, there are all sorts of things you need to kind of take care of and details to be aware of when you translate this high-level idea that I've just explained into something concrete that you can test. And there are all sorts of issues, in fact, with how TVLA does it and how FIPS 140-3 does it. Many papers have been written about this. And this is not what we were interested in. We were actually interested in the question that if you now follow such a non-specific detection process, which kind of gives you potential information leakage, Yeah, but it doesn't really tell you whether what you find could actually be turned into a concrete attack. So to give you an example, suppose you find indication there might be in the information leakage in the 5th round of AES. To exploit anything in the 5th round of AES, typically you would need already to guess all 128 bits of an AES 128-bit key. So this doesn't really seem to be an exploitable leakage in practice. So we were interested, can we add some form of a notion that captures exploitability and then also explainability, so turning the outcome of a non-specific attack to a concrete attack, can we somehow make this work? So this is really the problem that we try to solve with our paper. So now I'd like to just talk about how our kind of solution to this problem looks like. And our solution is based on 3 key ideas that we had. The first key idea is that in a process of non-specific detection, it would actually be very useful to define the input that we change to the device, not to be the plaintext input, but the key. So we fix the key, we fix the plaintext, and we then change the keys around. And this is in fact something that already the TVLA document somewhere in a side remark hints to, that this can be very useful at times. The second idea that we use is that typically the translation of this general principle of distinguishing 2 trace sets is typically implemented by some form of moment-based statistic. And we are sort of, in some sense, experts in my group in building regression models, and in particular nested regression models. So our second idea was, well, why don't we try and set up a model building-based detection test? And then the third key idea that directly then follows from using a model building approach was, well, if we kind of configure models based on parts of the key, which we call key chunks in our paper, then maybe this enables us to give some form of notion of exploitability, because the number of key chunks and the size of each key chunk in fact gives you an indication of the work factor of a differential side channel attack. And then finally, putting all these 3 kind of ideas in a sort of more generic framework where you do multiple steps, one at each time, perhaps enables you to add some form of explainability, where starting from a very non-specific detection initially, we kind of refine models in a way that eventually points towards a concrete attack vector. And these ideas they really relate also to some of our previous work. And we actually make all of this much clearer, of course, in the paper. So here I'm giving you a very sort of high-level, super intuitive version or view on the work that we have done. So let's have a look at this slightly more concretely. So I will not kind of torture you with too much detail here. So how does this kind of model building based approach look like? So a regression model always pans out to be a sort of multinomial in some variable of your kind of choice, in some explanatory variable of your choice. And as I said, we kind of use as variable that we then also vary as input chunks of a key. And the word chunk is quite undefined deliberately here. How you define a chunk has to depend on the architecture of the implementation that you're analyzing. So for a software implementation, a byte is a good chunk. For an ASCON, maybe a bit is a good chunk, or for hardware implementation, and maybe sometimes a 32-bit data word is a good chunk. We have 3 different examples in our paper, all with different chunks, as this seemed to be a great question of interest to the reviewers. So a full regression model is then basically a multinomial which allows for all possible interactions between the explanatory variables, so the key chunks. And a reduced model is a full model where we simply exclude some terms. And we can build different kinds of reduced models in with different complexities, down to a reduced model that actually includes no key information. And in statistical jargon, such a model would be called the naive model. So our generic, our non-specific leakage detection test then is basically based on the idea that we try and distinguish a full model from a naive model. If these 2 things can't be distinguished, given a data set, then there is no information about the key. in that data set, and otherwise there is. So this is sort of our non-specific detection testing. And by then defining different reduced models, we can then also hone in whether some identified leak, potential leak, is exploitable and how to explain it via an attack. So I make this slightly clearer by a toy example. So suppose we only have 2 key chunks, so an unrealistic implementation. But suppose we've only got 2 key chunks, then the slide here shows you how a full model looks like. So you've got 4 regression coefficients beta I, and then you've got the different terms, the different key chunks, K1 and K2, and there's only the interaction between K1 and K2, which is kind of encoded here in the model. And then a naive model would be no key information. So we then acquire a data set where we vary the key chunks K1 and K2 as an input, and then we would check, are these 2 models, can they be distinguished or not, using a suitable statistical test. If they can't be distinguished, there's no information about either K1 or K2 in the data, and if they can be distinguished from each other, then we know that there's information leakage. And then we could, for instance, ask, well, so what if we just remove K1? Do we still find the leakage? Or do we remove K2, or do we remove the interaction? And with that, we can sort of modify our test and learn a little bit more about what really leaks. And with that, I want to come to then the multiple steps that you would kind of do in practice. So the first step in our framework would be to do this full versus naive model testing. The second step in the framework would be to produce a reduced model of a limited degree. So the degree of the multinomial gives you an indication of how much work you need to do in an actual attack. So in practice, one would need to decide, okay, how much work can I afford? How many key bits can I guess simultaneously? And with that, you configure a reduced model and you check whether this still shows leakage. And then if you find, okay, I've got points which satisfy this condition, then you can go to the third step, and then you can ask which key bytes or which key chunks concretely give me the information leakage. And this gives you a kind of certificational attack. So to look at this very briefly on one of the examples that you find in our paper. So I chose one that perhaps most here would be familiar with. This is a kind of AES implementation in software on a typical 32-bit processor. 2 shares, so not very taxing. If it would be done correctly, there shouldn't be any leakage. This clearly is not done correctly. What we see here on this slide, on the top is a kind of representative TVLA outcome. So you can see TVLA also finds lots of leakage. On the bottom, you find the outcome from our test, how you would configure it in a straightforward way. And you can see you can also find a lot of leakage. Now we can ask the question, does any of these points really represent exploitable leakage? So is this realistic? So we would say we can definitely afford to guess 4 key bytes simultaneously. So we kind of repeat we repeat the model building, but only allow models of up to degree 4. And then we again apply this to all the trace points. What we can see here now on the top is the outcome for an entire 10-round AES. And what we can see is that from round 2 onwards, all the leakage requires more than 4 key bytes to be guessed simultaneously. So we would say this is not exploitable from our point of view. But in round 0 and round 1, there is plenty of exploitable leakage. We fix 1 point. This is the red star here in the bottom kind of picture. And now we see, okay, this is a degree 2 leakage. Now we can ask, okay, which key bytes really produce this leakage? And we then configure a test that only looks at pairs of bytes. We choose one. And we find out, okay, K0, K2 gives us, for instance, good leakage. And we turn this into an attack. Finally, the attack pans out correctly. So it takes a lot of traces, but it works. And we can, with a little bit of guesswork, we could also show a much more optimal attack, which is the picture here on the right. And with that, we sort of conclude the evaluation and say, okay, this device is clearly leaky and problematic. And this brings me to the end. So what we have is a kind of an alternative framework for leakage detection, stroke leakage assessment. It starts off in exactly the same non-specific way as TVLA, but then we can kind of narrow our model building to an extent where we can actually even come up with a concrete attack vector. And perhaps an interesting open question to pursue would be to kind of ask whether our technique could be implemented without using this nested regression model technique that we obviously use here, because the community's favorite model building approach is always deep learning at the moment. And it isn't clear to us whether our approach could be actually changed to work much more generically with all sorts of learning techniques. This brings me to the end. Thank you for listening.
So thank you, Elisabeth. Is there any question?
Hello, thank you for the great talk. I have a question regarding your approach, if we can also apply it for non-profiling attacks.
So the attack that we come up with in the end is inevitably a template-based attack. So because you get out key bytes that kind of are indicative of what leaks, the kind of the generic attack that we then configure is a template attack where you simply look at pairs of corresponding input chunk and key chunk. So without profiling, I don't really see how far you get.
All right, thank you so much.
Thank you. I was wondering, you're using kind of the number of bytes on which intermediate value depends as a proxy for exploitability. But you could imagine that even these middle bytes that depends on all the key, they can be exploited. Do you think there's a way to extend your work to cover that?
Potentially, yes. I mean, we really put this in place as a kind of as a replacement for the differential attack that ISO kind of replaces with this specific TVLA methodology. So we absolutely honed in on differential attacks, not on things like Saska. So to think along these lines would require to define exploitability in a different way. This is possible. We discussed different options, and we settled for this one because it's for differential input attacks.
Okay, thank you.
But we didn't think about it. It's another open question. You're right.
Okay, so there is no more question. Maybe let's thank Elisabeth again. So, yeah. So the third talk this morning is entitled Prover, Masking-Friendly Hash-and-Sign Lattice Signatures, and the authors are Thomas Prest, Thomas Espito, Guilhem Nio, Ron Steinfeld, Amin Saksak, Mohamed Esgin. And Guilhem will give the talk.
Yeah, so thanks for the introduction. So in today's talk, I will talk about Plover, which is a joint work between researchers from Monash and from PQShield. So yeah, when you design a signature scheme, there's basically a bunch of trade-offs you usually make. You have like a bunch of metrics you look at, typically the sizes, speed, portability, the security assumption you use, and one we sometimes forget, or that is not easy to implement, it's resistance against side channel attacks. So in the table below, you can see all the NIST finalists for signatures that are listed, and 2 additional signature schemes. You can see that the 3 finalists, they have, well, they all offer different trade-offs. They are not like perfect in for every metric, and in particular, they are quite bad actually at resistance against side channel attacks. It's pretty difficult actually to implement countermeasures in them. So that's when our work comes into play. So there's these 2 new schemes, Raccoon, Plover. Raccoon was a signature scheme proposed at the NIST call for additional signature scheme a few months ago. And Plover is this work. So both of them offer pretty good guarantees against side channel attacks. And the main difference between them is the paradigm. So you could see Raccoon as a sort of easily maskable dilithium, and Plover is more of a Falcon-like scheme. So let's now talk about side channel attacks, just a quick intro. So why do we consider all these all these countermeasures. It's basically when you put a device that runs cryptography in an untrusted environment, you can run a merge of physical measurements. And what was observed many times is that these measurements, they allow quite often to retrieve private material. So there's a bunch of ways to do this. Power consumption, electromagnetic emissions. You can also maybe measure the time to access the cache, and some more less typical one, acoustic emissions works also sometimes. So we can apply this, for instance, to the NIST finalist Falcon. There's been some work who did this in 2021. It's called Falcon Down. And what it looks into is the use of a floating point in Falcon. So I'm not going to go into details, but basically what they did is they ran a bunch of experiments, and they related this to all the floating point arithmetic. And these measurements allow them to directly retrieve the secret key. A second example on Falcon, which is more recent, it was published in 2023. So they look into a slightly different component of Falcon, and this time they don't learn about the secret key directly, but rather the dot product of the signature and the secret key, and they learn a direction of the secret key, and given that they make enough, they get enough of these measurements, they're basically able to retrieve the secret key in the same manner. So these two attacks were performed with power analysis. So now, what kind of countermeasures we have? A typical way to study countermeasures for this is to, we have a theoretical model that is often considered. It's called a T-probing model. So it's not perfect, but it's a good starting point. And what it does is basically you look at your signature scheme, you consider it as a circuit, and you allow an adversary to probe t-values in it. And the hope is that even if you probe these t-values, all your secret keys remain safe. And in this model, in order to be safe in this model, a typical way of a typical countermeasures is masking. So what you do is you take all your secret variables and you split them into oh, this is the whole set. Okay. So this is, you split them into D shares, basically. And if you have D, which is strictly bigger than T, the number of probes, then you can see that, so yeah, sorry, I got confused. So you split your secret into D shares, and the sum of these D shares, they sum to the secrets. And if you look individually at them, they look uniformly random. And if you probe strictly less than D, then you're not able to retrieve directly the secret. And in real life, this masking technique, it makes the cost of attacks scale exponentially in D. So it's, even if it's just a kind of theoretical model and not realistic, it has a good value in real life. So how do you implement masking in practice? So it actually depends on the kind of operations you want to mask. So if it's addition, it's pretty easy. You basically just sum sharewise your two values. If it's multiplication, it's a bit more complex, and you have a quadratic complexity in the number of shares. And if you want to implement more complex operations like comparison, then it becomes pretty costly, actually. So now, how about the two finalists? So we only consider here lattice-based finalists, Dilithium and Falcon. For Dilithium, there's some way to mask it, actually. But as you may know, it implements rejection sampling, so comparisons. And these operations have a very high cost. So it doesn't really scale well with the number of shares. And what we observe is that implementations will mask at order 2 with like 2-3 shares, but usually no more. And I told before about Raccoon. I mentioned it, and this is basically a dilithium-like dilithium, but what it allows is that you can scale D at a very well. You can mask your algorithm at a pretty high order. How about Falcon? For Falcon, there's actually no known way to mask it. It's basically because it uses floating point arithmetics, and yeah, there's been some work recently that tried to do it, but it's still quite far from being practical. Now let's look into solutions. How could we implement a Falcon-like maskable signature scheme? So I will skip this slide, they're not in the final version. So I would like to talk about Eagle, which is a scheme that was introduced in 2023. Sorry, I'll do this one. So let's look first at its signature algorithm. So it's a typical hash and sign signature scheme. So the first thing it does is hash the message into a point of z to the n. And then it does some Gaussian sampling. So it samples p according to some Gaussian. And then you can see a bunch of linear operation, then another Gaussian sampling. And then it just returns a linear combination. So far, it seems kind of hard to mask here because there's all this Gaussian sampling, so it's going to involve most likely some floating point arithmetics. But it's almost linear, as I observed just before. So yeah, the two hard parts are really the Gaussian masking. And from this observation, we designed Plover. And what Plover does is basically it just removes the complex variance matrix. So P is replaced by a simple Gaussian centered in 0 with a very simple standard deviation. It's constant. And Y is removed, so there's no Y anymore. It's just replaced by C1. And everything else is linear. So in order to also implement masked sampling of a Gaussian, we have this new function called addrep noise. So P is sampled from addrep noise, and then you have like very typical masked operations. So now I would like to look a bit more into addrep noise, to explain how we can sample a short vector with these algorithms. So as a column, you can see here, it's like, so you can see like steps of the algorithm. So it's like in each column, it's a step, or it's like the temporal evolution of the algorithm, and each column is just a sharing. So you can see the first step is like the 0 shares, and at each step, you basically add a small randomness to your input. And the hope is that you're going to sum many small values, and like your total value is going to be the sum of all of this. And the hope is that only a few are going to leak. So with this naive implementation for now, it doesn't work quite yet. There's already an attack in the t-probing model. So what you could do is you target one share, and you probe it at the start of the algorithm and at the end of the algorithms. And what you're going to learn is the sum of, in this example, 4 shares. So a significant number of them are leaking, so it's not very satisfying. But we can actually fix this by also adding some refresh gadget. So it's a very, it's a common thing for masking. And what it does is that each column now becomes independent. So in the previous example, the best attack was to probe at the start and at the end of the algorithm. And now, after you add refresh gadget, the best attack becomes to just probe individual randomness. So you can see that at most, you're going to learn t values. So most of the values remain safe. How about the security of this algorithm? So first, the output of addrep noise looks like a Gaussian. So it's just like a sum of many small Gaussians you could think. And another thing you could ask is, well, you remove all the Gaussian sampling, all the complex matrix used for variance in the algorithm. So now actually, Plover leaks a part of the secret key. But you can prove actually that it's quite safe. So there's a recent problem called hint-MLWE, which shows that even if you have signatures that depend on the secret, you can remain safe by increasing the size of the noises. So this is what we did. Basically, we have to increase the size of the noises by a factor square root of q. And then you can prove the security of Plover in the unmasked Plover. How about masked Plover? So as I told you before, there's a bit of leakage in add rep noise, but what we can do is we just write the noise. So here R would be P. You can think of P as being split into a safe part and a leaked part. And so the leaked part is not used for security, but the safe part has a very high, keeps a very high standard deviation because only a few small randomness leaked. So there's like a number here. So basically, rep was like the number of iterations in add rep noise. D was the number of shares. And if you observe that you have many enough iterations, D times rep is going to be much bigger than T. And basically, this value is going to be almost the total standard deviation of sigma P. You only have a small loss. So we can reduce the security of masked plover to unmasked plover. How about performance? So in this graph, we compare plover to masked implementation of dilithium. So we don't integrate Falcon because there's no implementation of masked Falcon. And well, you can see, I think it's quite clear that there's a high advantage of using plover over dilithium for counter side channel attacks. Even with only 2 shares, plover scales much better. So if you increase even more, 4 shares, 8 shares, you have a very significant speed gain. And now, how about the proof of the actual proof of add rep noise? So there's, yeah, like when you want to be more formal, so actually what you would do typically to prove security of the masked implementation of the masked algorithms, you would use the SNI framework. So normally you would like take some gadgets, so say multiplications, additions, and you prove their security when they're masked, and then you compose them all securely. The issue for us in this framework is that they only assume that you have inputs that are shared over D shares. And this is not the case in add rep noise, because part of the secrets are this small ri. So part of the inputs are not shared. So we introduced a new notion called SNI-EU, where U is unshared, and it covers this new leakage. Now, yeah, I'd like to conclude. So plover, so first, well, it's a new scheme that implements very efficient countermeasures for side channel attacks. But more than that, it also shows that part of this framework was, of all the techniques we used in plover, they were already used in Raccoon. And well, the addition of plover is first having a theoretical framework for the proofs. So Raccoon was a scheme that was not proven. So that's why we introduced TSNIU. And it also shows that all the techniques we use, so the replacing nonlinear operations with noise flooding and analyzing the leakage with HintMLDB works very well. So it's quite general. You can apply it to other schemes. And also, the use of add rep noise allows one to sample short vectors in a masked manner. So what are the advantages of these two schemes? So first, well, their resistance against side channel attack, it's the main advantage, and it's much faster than other schemes. And they both rely on like standard lattice assumptions. They're very simple. And yeah, the main disadvantage is their sizes, which is slightly larger than the typical, the finalists of NIST. And yeah, and I would like again to emphasize that all of these techniques can be applied to other schemes. And yeah, we leave this as future work. And I think it could be a very interesting question to have more schemes using this technique to have masking-friendly schemes. Oh yeah, thank you.
Is there any question?
Thank you. I just wanted to ask, which dilithium implementation did you compare with? Because if I get it, your scheme is using larger parameters, right? Because to avoid rejection and so on.
So it was, I don't know if I put the reference. I think not. So this was, yeah, okay, there's not the reference. So this was a paper really like looking into performance of dilithium. I don't remember the reference of the paper. But yeah, it's
everything, because it all depends what you mask in the end, right? Like I see something unavoidable is you need these additional Boolean to arithmetic conversions.
Yeah.
But that's pretty much it. And this, I don't know, did you benchmark the thing to see how much you spend on which part?
So I think it's included at the end, actually. Oh, wait. Oh, okay. This is not the right slide, set, sorry. But yeah, actually, we also benchmarked like individual parts. And most of the time, indeed, it's spent in the rejection sampling most of the time of the mask implementation of dilithium, I think.
And you masked the...
So it's not our implementation of dilithium. It's another paper that we took, and we just run it, and we compare it to our masked implementation of Plover.
Yeah. And do you mask SHA-3, or do you consider fresh randomness there?
I don't know exactly how they did it.
Like, if you mask SHA-3, I would say it's a bit artificial.
Yeah, no, I don't think they mask SHA-3. Like they don't need to.
Fresh shares, one leakage resilient.
You don't need to mask SHA-3, indeed, to have a mask implementation of dilithium. Well, you don't need to mask SHA-3, I think, to have.
It depends. Like the standardized versions, I guess yes, unfortunately. But if you make a new scheme, then you make a minor tweak to dilithium. You don't do it, and you gain a lot as well. And it's probably in between. Both.
Yeah, so I don't remember exactly, sorry, about how they did it exactly.
So you compared dilithium, masked dilithium against Plover. Wouldn't it be more interesting to compare Raccoon against Plover? So like, okay, so Falcon usually gives you more compact signatures than dilithium. How is it with the mask version? Do you reproduce the same relationship?
So yeah, it's quite similar actually with Raccoon. So I think Plover is slightly faster than Raccoon, mostly because we have simpler operations. But it's pretty similar, in fact. Yeah, like the gain is almost the same, I think. So like this work, it wouldn't be like whether we should like, I don't know, prefer Raccoon or Plover. I think it was more to have like a solution, to offer a solution for hash and sign, proves that it's something that we can also have an easily maskable for a scheme for hash and sign paradigm.
So thank you.
Loïc.
Thanks for the talk. I had a question on the slides where you present the attack with two probes and then how you fix it, right, so that you can only observe some of T short noises. So the slide right after. Oh, okay. Yeah. So I'm wondering because if you work on an arithmetic floating point and no longer on a ring or on a finite field, then would that mean that, for example, the remaining uncertainty on the secret, let's assume T is T minus 1, so you have only one share remaining, but if this share is also a short noise, then you may learn something on the remaining secret. And more generally speaking, my question is, are there any challenges from masking for dilithium, for example, over lattices, and when you go to arithmetic floating point?
So we didn't really consider. Actually, yeah, the floating point is very hard to mask in general. So all of this here is just arithmetic, like pure over ZQ, yeah. So there's nothing floating point. So that's also the point of these schemes, Raccoon and Plover. So there's no floating point at all. So yeah, over floating point, I think it's quite unclear, how you would perform this kind of algorithm, because there's no clear way, I guess, to mask it, unless like I guess you could do like more general techniques, but then it would be very costly.
And regarding the remaining uncertainty, if you consider only shares with short distribution, maybe I did not understand, so probably.
So you don't, so that's what the refresh gadget does actually. It basically makes everything uniform. So I don't know, say at this stage you run the refresh gadget and then all your shares look uniform if you take only T minus 1. So that's exactly what it does. Like because otherwise, yeah, you would have attacks. Like if you keep everything short, and yeah.
Okay,
yeah.
Thanks. Perfect.
Okay, so let's thank Guilhem and all the speakers of this session.